Hello everyone, welcome to Brain Blitz Audios. In this episode of NEET preparation, we'll be looking at previous year questions of chemistry in medical entrance examinations in India. We'll be looking at the first chapter of the syllabus of Grade 11 CBSE, and the chapter is Some Basic Concepts of Chemistry. Let's look at our first question. Temperature does not affect A. Molality, B. Formality, C. Molarity, and D. Normality. Now, for any of these quantities to be not affected by temperature, they should not have volume. So that means so in order to temperature to not affect, there will be no volume component. Let's simplify that by finding out the formulae for each of the components. Normality is the number of gram equivalents of solute divided by volume of solution in liters. Now C, normality, is proportional, whether inversely or directly. So here it's inversely proportional to volume. So therefore it is affected by volume, and temperature affects volume. So when temperature increases, the normality decreases. It's a similar story for molarity. Molarity is number of moles of solute divided by volume of solution in liters. So option D and C are incorrect. What about option B, formality? Formality is the number of gram formula masses divided by volume of solution in liters. So again, that is dependent on temperature, so option B is incorrect. The right answer is option A, molality, the one with an L, and this is the number of moles of solute divided by mass of solvent in kg. So here you see there is no component for volume, so the molality is not dependent on volume, so it's not affected by the temperature, while the other components are dependent on volume, so they are affected by temperature. Next question. The molarity of H2SO4 solution, which has a density of 1.84 gram per centimeter cube at 35 degrees Celsius and containing 98% by weight H2SO4, is 1.84, 18.4, 20.6, 24.5 molar. So here it's given 98% by weight. So that means in 100 gram solution, we'll have 98 grams H2SO4. And since the density is given as 1.84 grams per centimeters, we can find the volume using the formula. So here we know that density is equal to mass upon volume. So that means volume is equal to mass upon density. So the mass of the solution is 100 grams divided by the density is 1.84. So we can divide it like this. So 100 divided by 184, and we can then do the decimals later. And so 0.5, so that is 920, 80, and then 800, and then 4. So that becomes 736. And then that makes 640 and 3. So that means 552. So we'll get 88. So we can add another 4, 880, and then we calculate it. So after our calculations on division, we get our quotient as 0.5434 when we divided 100 by 184. But since we divide 100 by 1.84, we'll get the volume as 54.34 cubic centimeters. So now we need to find the molarity of this solution. So molarity is equal to the weight of the solute divided by weight, molecular weight, into 1000 divided by volume of solution in liters. So basically, this represents the number of moles of the solute, and this component actually was the denominator, but since we have to find the volume of solution in liters, and we have it in milliliters, so we divided it by 1000, and then it came to the top, so it became 1000 by volume of solution in milliliters. So weight of the solute is 98 divided by molecular weight. So in order to find molecular weight, let's do this. So H2, that's 2H plus S is 32 plus O4 is 64. So that's 34 plus 64, which is 98. So the molecular weight of H2SO4 is 98 into 1000 divided by 54.34. So 98 by 98 is 1. So we get 1000 divided by 54.34 molar. And that on calculation, you'll get the value 18.4 molar. So 18.4 molar is the molarity of the H2SO4 solution. So that is option B. So the right answer is option B, 18.4 molar. Our next question. So over here, we're given the normality of orthophosphoric acid. Orthophosphoric means H3po4, and it has a purity of 70% by weight, and it has specific gravity 1.54. Now we need to find the normality of orthophosphoric acid. So 70% by weight refers to the fact that in 100 grams of solution, we will have 70 grams H3po4. And specific gravity refers to density, which again is mass by volume. So volume of the solution will be equal to mass by density, which is the mass of the solution is 100, and our density, which is also specific gravity, is 1.54. So yet again, we'll have to do the division, 100 by 1.54. So 0 point, so that becomes 1000, and then 1.454 times 6 will give you 924. That makes 760. And then we can multiply 154 by 4. You'll get 616. And then you'll get 144. And then we add a 0, so we get a 9. So upon doing this division, we'll get our volume as 64.9 cubic centimeters. So now we need to find the normality of H3po4. So the normality of H3po4 will be the number of gram equivalents divided by volume of solution in liters. So that can be so number of gram equivalents is weight by equivalent weight. The whole divided by volume of solution in liters, but we have it in cubic centimeters, so we should divide it by 1,000. So that will be volume of solution divided by 1,000. So as I said earlier, this part goes to the top. So that means weight by equivalent weight into 1,000 divided by volume of solution. But how do you find the equivalent weight of H3po4? So equivalent weight is equal to molecular weight divided by the valency of PO4 minus. So the molecular weight on calculating, you get 3 into 1 plus phosphorus is 31 plus O4 is 64. So again, we get 98. So that is 98 divided by, since we have 3 H's and H has a valency of +1, and we know that the total valency of H3po4 is 0 because it's neutral. So then we can conclude that PO4 has a valency of 3 minus. So 98 divided by 3. The equivalent weight will be 98 divided by 3. And the actual weight is given here as 70% by weight. So in 100 gram solution, we'll have 70 grams H3po4. So weight by equivalent weight will be 70 divided by 98 divided by 3 times 1,000 divided by 64.9. Which on calculating we'll get 70 times 3 because 3 comes to the numerator, divided by 98 times 1,000 divided by 64.9. Now let's cancel some terms. So 70 and 98 both are divisible by 7. So 7 times 10 is 70, 10. 98 divided by 7 is 98 divided by 7 is 14. And then we can divide 14 and 1,000 divided by 2. So 14 by 2 is 7. 1,000 by 2 is 500. And so what we'll get is 10 into 3 is 30. 30 times 500 is 15,000 divided by 64.9 into 7. So 9 sevens are 63. 28 plus 6, 34. 42 plus 3, 45. So we get 454.3, which we can multiply 10 on both sides. So we'll get 15 divided by 4543, which on division, you'll get 33.01, and then there are some more terms. So the closest value to 33.01 right now in our options is 33. So we can write 33, option C, as our right answer. So our final answer is 33 normals. Now we move on to our next question. The weight of one molecule of a compound of molecular formula C60H122 is. So our formula is C60H122. So we can calculate the molecular weight. So that is 60 times the mass of carbon. So that's 12 plus 122 times mass of hydrogen, which is 1. So 60 times 12 is 720 plus 122 times 1 is 122. So 720 plus 122 is 842. This is the molar weight. Now what we need to do is we need to find the weight of one molecule. So 6.02 times 10 raised to 23 molecules weigh 842 grams. So one molecule would weigh 842 divided by 6.02 into 10 raised to 23 grams. So let's calculate. So that's 842 divided by 6.02 into 10 raised to 23. So then what we can do is we can convert 6.02 into 602 into 10 raised to 21. And since 10 raised to 21 is in the denominator, in the answer, it'll be 10 raised to minus 21 times 842 divided by 602. So 602 goes once, so 1 will get 240 on subtraction. So now what we do is we put a point decimal here, so we'll get 2400. And so in 2400, 602 goes 3 times, and I can prove that 602 times 3 is 1806. And so 1806, and then on subtraction, we'll get 594, and then again, we'll put a 0. So 602 times 9 will be 5418. So we can put a 9 there, and we do 5418. So that is 10 minus 8, 2, 4 minus 1, 3 minus 1, 2, 9 minus 4, 5, and 0. So we have a quotient 1.39 and 522 as the remainder. So let's write the quotient here, 1.39 into 10 raised to minus 21. But we can reduce this because 9 is greater than 5. We can write this as 1.4 into 10 raised to minus 21. And that is equal to option C. So option C, 1.4 into 10 raised to minus 21 is the weight of one molecule of a compound having the formula C60H122. Next question. During the electrolysis of water, the volume of oxygen liberated is 2.24 decimeter cube. Decimeter cube is just the same as liter. So the volume of hydrogen liberated under the same conditions will be. So in order to answer this question, we should write the formula for electrolysis of water. So H2O gets converted to H2 and O2. And we use stoichiometry to get the formula to H2O on electrolysis, giving 2H2 plus O2. So 2 moles H2O gives 2 moles H2 and 1 mole O2. And so 2 into volume of H2 will be the same as 1 into volume of oxygen. So what this equation shows us is that the volume of hydrogen will be twice the volume of oxygen, because there is a 2H2 and there is only 1 O2. So now when we know the volume of O2 as 2.24 decimeter cube, we can calculate the volume of H2 as 2 times 2.24 decimeter cube. So let's multiply 224 divided by 224 multiplied by 2. 4 times 2 is 8, 2 times 2 is 4, 2 times 2 is 4. So we'll get 448 decimeter cube as our answer. And since there's a decimal here, we'll put it here. So it's 4.48 decimeter cube. That is option C. So option C is the volume of hydrogen liberated under the same conditions. So that is 4.48 decimeter cube. Next question. The reaction of calcium with water is represented by the equation Ca plus 2H2O gets CaOH twice plus H2. What volume of H2 at STP would be liberated when 8 grams of calcium completely reacts with water? So you see 1 molecule of calcium gives 1 molecule of H2 as the product. So 1 moles of Ca will also give 1 moles of H2. The ratio stays the same. 1 mole of calcium has the mass 40, so 40 grams of calcium. And that gives, and since we need to know how much volume of H2 is liberated, for 1 moles of any substance, they have the volume 22400 centimeter cubic centimeters. So 22,400 cubic centimeters of H2 is liberated by 40 grams of calcium. So using unitary method, we'll know that 1 gram of calcium will give 22400 divided by 40 centimeter cubes H2. And when we multiply this by 8, so we'll get 8 grams of calcium, which is the value given in the question. So 8 grams of calcium completely reacts with water to give what volume? That volume is 22400 divided by 40 into 8 centimeter cube of H2. So let's start calculating so the volume of H2 liberated. So that is 22400 divided by 40 times 8. 8 goes into 45 times. 8 times 5 is 40. So it goes into 45 times. So that is 22400 divided by 5. So again, 22. So that's 4 times 22, 24. Again, 4 times 4. And then there's 40. So that's 8 times 0. So we'll put a 0 there. So the volume of H2 liberated will be 4480 centimeter cube. And if we go back, we find that option D is the right answer because it has the value 4480 centimeters cube, which is the value that we got by calculating. Now we come to our final question. No, this isn't the final question. We have another question after this. So let's look at this question. Which of the following pairs of solutions are expected to be isotonic with temperature being the same? So that's the common condition. So we have pairs of solutions. So how do we solve this question? So for two solutions to be isotonic, their osmotic pressure has to be equal. And the value of osmotic pressure is given by molarity times number of components in a molecule. Let's look at each of our options one by one. So in option A, so we have 0.1 moles of glucose. Glucose is C6H12O6. So that is moles of C6H12O6. So then we have 6 grams of, so we have 6 atoms of C, 12 atoms of H, and 6 atoms of O. So that totally makes up to 24 atoms in that molecule. So 0.1 times 24 is the osmotic pressure, which will be equal to 2.4. The value will be 2.4. But let's look at our second component. So that's 0.1 molar of C6H5 and plus H3Cl minus. So that has six atoms carbon plus 5 atoms hydrogen. So that's 11 atoms plus 1 atom nitrogen, that makes 12, plus 3 atoms of hydrogen, that makes 15, plus 1 atom of Cl, that makes 16. So 0.1 into 16, which is 1.6. So as you can see, these are not equal. So this option is wrong. Let's look at option B in the similar way. So that is 0.1 molar NaCl. That is 0.1 into NaCl has just one Na and one Cl. So that's 2 in the formula. So the value will be 0.2 for osmotic pressure. If you look at 0.05 molars of BaCl2, we find that it's 0.05 times 1 Ba 2 Cl, so that's 3, so we get 1.5. Again, these are not equal, so this is incorrect. Option C, 0.1 molar Na2SO4. So that is 0.1 times 2 molecules of Na, 2 atoms of Na, 1 atom of S, 3 plus 4 atoms of O, so that's 7. So we get the value 0.7 osmotic pressure. Now we compare that with 0.1 molar KNO3. That gives 0.1 into 1K, 1N, so that's 2 plus 3O, that's 5 atoms. So 0.1 times 5 is 0.5. Again, these are not equal, so option C is incorrect. Let's prove that option D is correct. So 0.1 molar BaCl2. So that is 0.1 times 3 because 1 Ba 2 Cl, so that is 0.3. And our next one is 0.75 FeCl3. So that is 0.75 times 1 Fe 3 Cl, so that's 4. And 75 times 4, 27 4s 28 plus 2 30, so that's 300. So 0.75 will give you 0.3. Let's check that. So it's 0.075 FeCl3 and 0.1 molar BaCl2 have the same value of osmotic pressure, 0.3. So that means option D is the right answer. Now we come to our final question of this episode. For preparing 0.1 normal solution of a compound from its impure sample, for which the percentage purity is known, the weight of the substance required will be less than the theoretical weight, more than the theoretical weight, same as the theoretical weight, or none of these. What is theoretical weight? So theoretical weight is the weight required to form a solution from pure sample. So that is theoretical weight. But over here, the impure sample has the compound plus impurity. And in the solution, only the compound goes into it. The impurity has no role. So that means we have lesser concentration of the compound than in a pure sample. So we need more of the impure sample in order to match the weight required to form the solution from the pure sample. So therefore, option B is correct. If it's less, then the normality of the solution will still be less. And if it's the same, also the same scenario. So options A, C, and D are incorrect, and option B is the right answer, simply because there is an impurity in that compound, in that sample, and the impurity does not go into the solution to form 0.1 normal solution of that compound. So therefore, option B, more than the theoretical weight, is the right answer. And that ends this episode of NEET preparation. We hope you found this video interesting. To access more of our useful and interesting content, please visit our YouTube channel, Brain Blitz Audios, and subscribe to our channel. We'll be back with more useful, interesting, and education content such as learner words, mind maps, CBSE board exams, NEET preparation, etc. So until then, take care, stay safe, ta-ta for now.